All right, let's talk about Lab 8. You'll notice that our lectures are getting a little bit shorter now because I want to make sure you have enough time in addition to learning all this new stuff that I'm teaching to like work on your labs and work on your final project especially. All right, so let me give you a new lab and it'll be a multi-week lab so you have time to work on it as well as your final project. All right, so let's get into it. Here's the write-up. This one's about image processing. So it's pretty much, you'll go back to the lecture where I did the image processing, and it's going to be very, very similar because I kept stealing code from here, from this lab. It's lab 8, okay? So here is the secret. Let's talk about it. So here are the things you're doing. Your filter.cpp is like the main function. It's taken everything over, and then we're giving ourselves the ability. If you go to filter.cpp, we're giving ourselves the ability to take an image, like we're getting it through command line arguments. We're getting an image name in addition to an operation, like an output image name. We're giving ourselves the options to either like convert our image to grayscale, so like black and white shades of gray, as well as darkening the image, which is kind of cool. And so I'll show you both of those and what your program should look like and how it should work. So I've taken care of everything. I've taken care of to make sure like I'm reading these bitmap files. Like I've given you a couple bitmap files that I'll be testing you on. Like you have the picture of my cat like I used in lecture. All those things you have, and so you can test on those. But I've taken care to read those bitmap files in the right way and make sure to like call your function on each array of pixels and make sure that those pixels are multiples of like 16 bytes, even if they weren't really, just to make sure that you can use your fancy 128-bit registers if you want to. So that's the goal, and that's honestly what I'm forcing you to do anyway. So yeah, just like, you don't have to understand filter.cpp too much. It's just going to make sure to call your function on each row of pixels in the image that you pass along. Okay? So that's what's going to happen. And so the bulk of your work, all of your work, is going to take place in these two S files. So darken.s and gray.s. Okay? So let's talk about each of them. So yeah, the user's given you a command, filter or darken. And then you also give like the input file and the output file as well. So go back to the way that I was running it in lecture if you want to see that. But yeah, either one of these two functions, grayfp or darkenSIMD, will be called for each row of pixels in your image that you pass along. And I have made sure, I've guaranteed that your filtering function will get a multiple, like an array of pixels, and that array is guaranteed to have a multiple of 16 of size, okay? Even if that wasn't true for the original image, I am saving you a whole lot of work right now, okay? So that's the goal, and that's what's going to happen. So yeah, the very first thing I want you to do was like pick one. Pick one, which one do you want to do? Let's do grayscale with floating point assembly. So this is an example. I'm forcing you to practice your floating point assembly as well as your SIMD assembly. And so this first one, this grayfp function that you're going to write, here is its signature first of all. And you are not going to use SIMD operations. You're just going to use floating point operations for this one, because here's what I want you to do. I would like you to convert your pixels. You're getting this many pixels starting here, an array of bytes, starting there, to grayscale. All right, and what I'd like you to do is calculate the following value called grayscale value, and you'll have to like round it to the nearest whole number. I'll show you how to do it in just a second. But what I want you to do is, given your pixel, you get red, green, and blue for each pixel, right? And remember the order of everything. It's a little bit backwards. So as you get your array, it looks like this, right? It's going to be in memory. It's really backwards. It's BGR. The first byte is the blueness of the first pixel, then the greenness, then the redness, and then the second pixel goes at BGR order again. Okay, so that's the goal. So figure out those values. You're going to have to get them into floating point registers so that you can multiply red by exactly that, green by exactly that, and blue by exactly that. And then round your result, whatever you see, to the nearest whole number. So you'll get a value between like 0 and 255 in theory, right? Use double precision floating point for your calculations. So use D registers rather than S registers, all right? And what I want you to do is change the red, green, and blue channels of that original pixel that you did this and calculated this for to whatever grayscale value was, all right? So say that like you got this particular pixel value. Let's see, do I have an example here? Let's say, yeah, here's a good example. So let's say that you were given, right, you're given this. You're given this pixel, red 212, 74, 87. All right, 212, 74, 87. And this is red, green, and blue in that order. That's the standard order. But really, you're going to read it backwards, right? Red, green, blue. So get red, green, and blue like that. And your goal is to convert it to grayscale. Remember that like shades of gray in RGB are when the red, green, and blue are the same. So like this is black, 0, 0, 0, all the way to 255, 255, 255. That's white. So as long as they're all the same, it's a shade of gray. And that, I could have drawn this better. I got the digits out of order even. There. So yeah, as long as they're equal, the red, the green, and the blue parts are equal, it's the shade of gray. If they're not equal like this, it's not a shade of gray yet, it's some color. So your goal is to calculate this grayscale value and replace each red, green, and blue with this thing, with this rounded thing, all right? So you're going to perform that calculation and replace the pixel with, instead of its original red, green, blue, with grayscale value, grayscale value, grayscale value, okay? That's the goal. So if you saw 212, 74, 87, you're going to calculate this grayscale value, 104.27, and then you'll round it to the nearest whole number, which is 104. And so your goal is to translate this pixel into 104, 104, 104. Does that make sense? It's very similar to the black and white example from class. So go and look into that one. It'll be similar. And yeah, you'll be using the make file to compile. You can just say make to compile the whole thing. And then you'll run it with the /filter, all right? So in it, I'll show you how it should look in a second. Let's go back to the assembly. So yeah, here are some hints for you, all right? So remember that floating point assembly is not SIMD assembly. You could if you wanted to. There's a way to do floating point SIMD, but it's not really worth it. I just want to get you practice with floating point only right now. So you're not going to be able to work on multiple pixels at a time. You're going to do one at a time, all right? You're going to read your current blue, your current red, your current green, not in that order. Current blue, current green, current red. You're going to read 3 bytes for your current pixel, right? That was 1 pixel. Maybe you should subtract 1 so you know when you're done, right? So that's the goal. The colors are in blue, green, red order, not red, green, blue order. You'll read a single color at a time for a single pixel. You're going to have to read it into an int first. So that's a load byte, right? It's not a character technically, but it's 1 byte value. So read a byte at a time with load byte. And then here is how you put that into a floating point register. Put it into a D register with this command. So in the floating point assembly lecture, I did give you a link to the documentation page for all these, so you could look this up. But this stands for unsigned convert into a floating point value. All right, so you'll like use this with the D register and whatever W register you loaded your byte into. All right, so like put the red in a double register, put the green in a double register, put the blue into a double register. Do your calculation. You'll probably need to use the data section maybe to put these constants somewhere and read them in, just like I was doing in like the midterm 2 review with pi. And so there's that. And then to do the rounding and convert it back into like a W register, you'll do this. It's F convert AU, all right? So look up how to use that instruction in the documentation, and that will do the rounding. It converts it and it rounds it. The AU, I forget what it means, but it just means round it to the nearest, number, not round like down always or something. And then it converts it back. You can put it into a W register after that, all right? So yeah, look into those instructions. Just go to the documentation pages. It should be more or less self-explanatory, but that's what you're going to do for each pixel. And so every time you process a pixel, you've worked on 3 bytes. You should advance maybe that by 3 bytes, and then you've worked on a single pixel at once. So you've got to get that all the way down to 0, all right? So that's the gray function, gray FP. All right, and here's what each of those files that I gave you should look like. So nice and grayscale valued, all right? So it's cool that you can do like floating point calculations, and that like it corresponds to how our eyes see light brightness. Kind of like green is very important for our eyes, apparently. That takes a lot of precedence when it comes to like converting to grayscale, to black or white, which is interesting. All right, yeah, our eyes like the color green apparently. So yeah, next, the other example is I want you to use SIMD, those neon SIMD assembly operations, to work on a bunch of pixels at once and darken them. All right, so this is the darken SIMD function. So here's this one. And so your goal is, again, you're given a bunch of pixels, the start of an array of pixels, and this is how many there are. It's guaranteed to be 16, so you can use your V registers, which is nice. And what I want you to do to darken them is I'd like you to cut their channels in half, all right? So cut the red, cut the green, cut the blue in half. That will darken it because it'll make it closer to 0, right? So like if you saw like 64, I'm just going to use powers of 2 because it's easier for me. 64, 128, 16. If that was your input pixel RGB, your output pixel RGB needs to become 32, 64, 8. Do you see how that made it a bit darker? And that's going to make it closer to black, and that's one way to darken an image. All right, so that's what I want you to do. Read in the red, green, blue channels. Remember that it's going to be BGR order, sadly. Remember that. And then just like divide them each by 2 using integer division. All right. So how can you do that with your SIMD instructions? There is no divide. See if you can figure it out. There's a way to do it. Divide it by 2. So yeah, for example, if this was your input pixel, then you're just going to like divide it by 2 using integer division, computing this pixel. All right. And then that's the one you write back. All right. Red, green, blue in the right order, of course. So remember that you get BGR order in the real image file. All right. So you can use my neon SIMD example from class to like read everything, read the red, the green, the blue, not in that order though, into your V registers. You can get 16 at once that way. And you can do this, like you can work on 16 pixels all at once, which is really, really cool. Work on them, write them back. All right, so here's what each of those sample images should look like when they're darkened. And it's a little bit hard to kind of see that, because like you're on the terminal, you're outputting an image file. I can teach you. There's a couple ways to get it off of your computer. There's an SCP command to copy it back onto your computer if you're on a Mac, or there's a program called CyberDuck. You can look into that to like get your files off of your home folder on the class server. There's also that, or if you're on Windows, you can use WinSCP as well. But CyberDuck is Windows or Mac. WinSCP is only for Windows. That's just like a program that you can download. But SCP is a terminal command if you have access to the terminal on your own computer, like you installed Windows Subsystem for Linux or you have a Mac. So that's another way to do it. And I'd be happy to help you like download the images like onto your own computer so you can actually look at them. All right, because that's going to help you compare and see like, did I do the right thing? Because the images will look really cool even if you mess up. I can promise you that. But it's going to be useful to see the answer. Does it look right? All right. So yeah, that's I think all that I wanted to say. Yeah, you know what to do. You're going to work on 16 pixels at once if you're going to use V registers. So remember that you're going to have to like advance your pointer, subtract this in the right amount. You'll figure it out. All right, I believe in you. So yeah, that's your fun image processing lab, probably the most fun lab of the semester, I would say. It depends on how you feel, but I think it's one of the top ones for sure. I'm proud of it. And so yeah, you're only going to be messing with those functions, so you're just going to turn the assembly files that you worked on. Okay? And yeah, you got a little while to do this, so check that due date, but it's more than just a week. All right? So yeah, go forth, prosper, good luck, and let me know if you have any questions. I'll see you later.